Modern physics. Modern physics is typically defined as the physics that came about when classical physics stopped working. So, classical physics, not that it stopped working, but around the turn of the 19th, 20th century, there were some major issues that started coming up with classical physics because technology got so good that we could dive deeper into atoms or look deeper into space, and some of the phenomena that we started seeing didn't necessarily match up with what we were expecting according to classic physics or just generally accepted facts of the universe. So, today's lecture is going to talk about one in particular, which is known as the wave-particle duality. So, we remember this, hopefully, from when we did waves. So this is what's known as the double-slit diffraction experiment. Now, they did this with light waves. So what we have here going on here is light. So, for instance, monochromatic light, so a laser of some kind, shown onto two slits. Now, when it goes through a slit, when it goes through a gap of some kind, it diffracts. So it does this guy, right? Starts to bend. And because we're sending it through two of them, it bends towards itself, right? So when it bends towards itself, it obviously ends up at some point in the same area at the same time. So we got this point here where this entire line represents a line where constructive interference is happening. Because if you look, you got a crest and a crest, a crest and a crest, a crest and a crest. If you look really carefully, technically this point here is where a trough and a trough are. Trough and a trough, so on and so forth. So that's a point or a line along which constructive interference is happening. Same thing here and here and here. So if I erase this, if I erase this and you pause the video for a second or two, you can look at it really carefully and prove to yourself that those are lines of constructive interference. Okay? Now, the lines in between are lines of destructive interference. So if you look, let's say here, here, that's a point where a crest and a trough run into each other, and when destructive interference happens, the light goes away, which is why at the spots in between here, we have black space. Okay? So we have this pattern, which was used to prove that light was, in fact, a wave, acted like a wave, because light goes through here and does only things that waves do, which diffraction and interference is things that only waves do. Well, then light must be just a wave. It should always act just like a wave. Now, the thing that got a little wonky is later on, they started to realize that maybe the picture wasn't so easy. So what they realized later on is the fact that particles, when sent through a double slit, also act like this, also make a diffraction pattern or interference pattern. So when they did this experiment, and we talked about this, I showed you a video on this, if we send electrons, little particles, through here, and I'll post a link to the video for this again so you guys can see it. You send these particles through there, they also act like this. So they also act like a wave. So this is the first part of wave-particle duality. Waves obviously act like waves. So the experiment for light was, well, pretty classical, right? Because waves acting like waves, we expected light to be a wave, and it acted like one. The modern physics-y part of this was the fact that when we sent the particles through, they too acted like waves. So wave-particle duality just means that waves can act like particles, and sometimes particles can act like waves. And obviously waves act like waves, and particles act like particles. So in a situation like this, this experiment proves that waves act like waves, but sometimes particles act like waves. Now, our next screen. So for our next screen, we need to just remind ourselves of how a capacitor works. So a capacitor is a thing that is meant to store charge. So here I have the capacitor hooked up to a battery. The battery sends electrons up here, and they get stored on this plate. Now, when this plate is filled, no more current is going to flow out of the battery because the electrons have nowhere to go. Now, this plate, which is supposed to be closer, but for the sake of the picture and drawing on it, I wanted to make sure they were a little bit further apart. But what happens is these plates are so close together in reality that the electrons on this plate get affected or pushed off of the plate by these electrons because they don't want to be near each other. And those electrons flow here, and they go into the positive side of the battery. Now, eventually, when this is completely filled, this was going to have as many electrons leave it as it could possibly have. So this ends up being permanently positively charged, and this is negatively charged. And because it's stopped having electrons leave, there's no current flow in this leg either. So eventually it gets to the point where these are fully charged and there's no current flowing through the circuit. So if I put an ammeter here, it would register no current. With me. Okay. Now, going to the next page. This is a similar setup. Now, this is a setup of what's known as the photoelectric effect, which was an experiment set up to prove whether or not light actually has momentum. Because light has momentum, then you could argue that at times light acts like a particle. So they have the capacitor, they have the battery, they have the negative plate, they have the positive plate, and here they have an ammeter. So if they just let this thing charge up in the absence of light, eventually this gets to the point where it's charged, this gets to the point where it has the equal but opposite charge, and there's no current in here. Okay, now, what they did is they then shone light on the electron plate. So light came in here, and they made it more and more and more intense, and nothing happened. So then what they did is they changed other characteristics of the light. For instance, frequency. They increased the frequency, and they found that at some specific frequency and above, electrons started breaking off, going here, and running through the ammeter. So what did this prove? This proved, lo and behold, that light had momentum. That light was breaking off electrons, and the only way it could do it is because that electron was being collided into by light. So this slide kind of explains what was classically understood versus what changes had to be made. So classically, we understood that light was this massless thing and should therefore have no momentum and have no kinetic energy, at least in the formal way of having kinetic energy wherein it can knock into things. Now, what changes had to be made? Well, the change that had to be made was we had to be able to now say specifically that light can sometimes act like a particle. So something that is a wave can act like a particle. So that's where this wave-particle duality thing kind of finishes up, because we've now proven that waves act like waves and particles act like particles, which is obvious. We proved that a particle can act like a wave, and now we've proven that a wave, specifically a light wave that is thought to be massless, can act like a particle, which is something that has mass. Now, fun fact, Einstein has a Nobel Prize. We all know him as probably the most famous physicist out there. But his Nobel Prize is not for what you think it is. His Nobel Prize is not for the E equals mc squared that we all are aware of, although we will talk about that later on. His Nobel Prize is for explaining the photoelectric effect, coming up with a formula that relates the frequency and the energy of this thing, and coining the term photon, which is the term that we use for a particle, and you can't see me, but I'm doing quotations, a particle of light, because light is a wave, but occasionally can act like a particle when, for instance, colliding with electrons. So, this is our formula. Sorry, those of you who were on the Zoom call earlier today heard me say that I had some technical difficulties the first time I recorded this, so this is the fourth time I'm recording this, so hopefully fourth time is a charm, but that's why I had to erase everything. So this is our formula, E photon, so the energy of a photon is equal to H times F, or it's equal to HC of a lambda. So first things first, C we know already, C we worked with when we did waves. E is just the energy. Now, this energy is going to be in joules. F is the frequency. That will be in hertz. Planck's constant is a number that's on the front of your reference table. 6.63 times 10 to the negative 34 joule seconds. and wavelength is just wavelength, and that'll be in meters. Now, why the two formulas? Well, it has to do with the fact that whether or not they gave you the frequency of the light or the wavelength of the light. And they basically work together. It makes sense that they are one and the same, because we look at this formula, V equals lambda F, and we say that we know it's light, so we can say the V is going to be the speed of light, lambda F, and then we solve for F and we get C over lambda. If I just take out F and I put it in for C over lambda, or rather if I take out F and I put C over lambda in for it, I end up with that formula. All right, so here we have a simple enough question. We have the question of how much energy does a particle of light, a photon of light with this frequency have? Now, why am I asking specifically about that frequency? Well, that frequency, if you remember, is the frequency for the index of refraction chart that we have on our reference table. And no, we're not going to go back to Snell's law and refraction and all that stuff, but if you remember really carefully, this frequency also represented the frequency of light that was kind of right smack in the middle of the visible light spectrum. So it's a pretty interesting one to know the energy for. Okay, so we're going to say E equals HF. We're going to say E equals 6.63 times 10 to the negative 34 joule seconds. And the frequency is 5.09 times 10 to the 14th. Try that again. 10 to the 14th hertz. And then we do the math. So I'll give you a second or two to do the math. And you end up with 3.37 times 10 to the negative 19 joules. Okay, so that's how much energy a single particle or photon of light with that frequency would have. Now, because a joule, in terms of electrons and atomic stuff, is a really large amount of energy, they oftentimes will work in electron volts. So, just a quick reminder about electron volts. We talked about these when we did electricity. It is defined as the amount of energy required to move one electron through 1 volt of electric potential. You don't need to know that for this particular part of the chapter. You just need to know that it represents a smaller, significantly smaller amount of energy than 1 joule. Okay? So if I want to find out how many electron volts of energy that energy we had on the last page was, nope. We're just going to do this. We're going to say 1 electron volt is 1.6 times 10 to the negative 19 joules. And how many electron volts is 3.37 times 10 to the negative 19 joules. You're going to cross multiply. You're going to get x times 1.6 times 10 to the negative 19 equals 3.37 times 10 to the negative 19. Then you are going to divide both sides by 1.6 times 10 to the negative 19. 6 times 10, 19. Those go away. And when all is said and done, you get an energy of 2.1 electron volts. So reasonably simple. Now, because this was a short lecture, you can assume, or you can safely assume, that the assignment will be short because we only have the one equation and some conversions to do. So today I will post this. I will post the assignment. It'll probably be 10 to 15 questions. So try to have that done by Thursday, because we're going to post another lecture that's going to be a lecture on the applications of this. So applications of this are huge and far-reaching, but I figured we'll try to do something short, quick, kind of get our brains back into physics, and then we'll get to the applications of this on Thursday rather. All right? So hopefully all is well, and I will talk to you guys soon.